Great. Well, thanks everyone so much for coming to the next installment of the UCL Dark Invited Speaker Series. And it's my great pleasure to introduce Jakob Andreas today, who's going to speak to us about grounded language learning without grounded supervision.
Sorry, there's a Zoom thing in the middle of my screen that I don't seem to be able to dismiss. Let me fix that. Okay, working now?
Yeah.
Okay.
So yeah, Jakob is the ex-consortium assistant professor at MIT, and his research focuses on building intelligent systems that can communicate effectively using language and learn from human guidance. And as I said, he's going to talk to us about grounded language learning without grounded supervision. So Jakob, over to you.
Yeah, thanks again for having me. Obviously, wish I could be there in person, but this is nearly as good, and looking forward to talking with those of you who I have meetings with later. So, as the title suggests, this talk is broadly about how we can do better grounded language learning without having the kind of data that we customarily assume we have access to for grounded language learning. And what do we mean by this? Well, right, there's a lot of tasks that we think about in NLP that are basically about using language to interact with the outside world in some way, right? Whether that's sort of gaining information from sensors or giving instruction to interactive agents, or even sort of explaining the decisions of various kinds of deep learning models. And so, at some level, it's going to be super important to have representations of the language that can interface with representations of the world more generally. And even in NLP tasks that sort of superficially just involve text, things like language modeling, right? These tasks really are still about the outside world. If you look at something like a recipe, you're trying to do recipe generation, you still really need to have a relatively fine-grained understanding of sort of what objects are and how objects interact with each other in order to do this text generation effectively. And this is a problem because on one hand, getting text data is cheap, and getting information sort of about how the world works in the form of unlabeled images or unlabeled videos, or maybe even, sort of examples of people interacting is comparatively cheap, but data that actually combines both of these sources of information is relatively precious, is typically not generated by kind of natural processes in the way that text is generated or images are generated alone, and is really one of the largest bottlenecks to building models that have kind of general purpose language understanding capabilities. And so what today's talk is about is building better models for these kinds of text plus interaction tasks, using only one of these sources of supervision or the other, or if not, sort of building these models from scratch, then at the very least, sort of taking models that have been trained on a little bit of this precious grounded language data and either using sort of pure experience without extra language or pure language without extra experience to make those kinds of models better at understanding language in the sense that we really care about. With the usual caveat that this sort of nice framing is in fact just a justification to talk about two papers that I wanted to talk about today.
I have maybe just a silly definition question, but
yeah.
About, okay, I get the paired data isn't available. What does grounding on its own mean? I maybe naively would have just assumed that grounding was, is it the actual facts or entities without the text being aligned to them? Because grounding, yes, I've never heard it used without talking with regard to something like text or expressions.
Yeah, maybe this is an abusive grounding, and a more precise thing to say here would be like interaction with the world or perception of the world without accompanying text.
Okay, I see. Thanks.
So the thing that we are trying to ground into. Good. And the first part of this talk is actually going to be about exactly that, about what we can do with interaction with the world to make us better at understanding text. Main piece of work here is done by my student Jakob in collaboration with Mike Lewis, who's at FAIR in the US. And the sort of high-level setup for this part of the talk is what's known as the options framework. So this is, in reinforcement learning problems, and in particular in reinforcement learning problems that involve a lot of sort of high-level planning or long-term reasoning. One idea that's come up over and over again is that it's useful to have hierarchical representations of policies, right, where your agent can decide, I'm going to take some sort of high-level action like move into the next room or, you know, boil water or something. And only after figuring out the sequence of high-level actions that it ought to be taking, figure out how to ground those high-level actions, figure out how to translate those high-level actions into sequences of low-level actions that are sort of directly executable in the environment. There's a lot of work in the kind of general RL literature on learning these kinds of policies in a sort of relatively unstructured model agnostic way, where you just have some sort of discrete space of high-level actions without any semantics initially built into them, and you jointly learn what those things should be and how they should be implemented, you know, or rather directly against your reward function. And one of the things that has happened in the last couple of years at kind of the intersection of NLP research and RL research that's been really exciting is the development of these kinds of option style policies where these high-level actions are not unstructured discrete task identifiers, but are actually natural language strings, and where we build agents whose way of interacting with the world is basically first to like look at the state that they're in, figure out, or rather generate a natural language description of what it is that would be appropriate to do at this time step that would accomplish their long-term goals, and then translating that natural language description of their high-level goal into a sequence of low-level actions. So models that really sort of plan about how to interact with the world by first generating instructions for themselves to follow, and then following them and seeing what happens, and then replanning as a result. And so this is something that you can do, and something that was really proposed like by a bunch of people independently around the same time, and turns out to be quite effective at a bunch of tasks involving this kind of high-level reasoning. And you know, all kinds of applications for these things. You can, if you just think of like having one high-level task that you're trying to infer or accomplish, use them for text editing tasks. We have some recent work that I'm not going to talk about today, but would be happy to discuss later, where you actually do program synthesis by decomposing programs into bits that you have natural language descriptions for. But a more kind of prototypical example, and in fact, the one that I'm mostly going to be talking about in this section of the talk, looks more like this, where you have like really, really low-level actions that say involve moving agents around on a grid, that are going to be associated with high-level goals. And you're going to generate a sequence of these high-level goals, maybe dynamically and responsively to the current state of the environment, in order to accomplish some more generic task like winning a game. So here, in fact, is an example of the agent that we're going to be discussing how to build in this section, which plays a real-time strategy game, a game that works a little bit like StarCraft, by, you know, in this manner that we described, by generating instructions for itself to follow and following them. And so if we start this off, in a minute, it's going to zoom in on what our player can actually see. And you can see that it's generating instructions like build peasants, send peasants to the mine. And at some point, it's going to start changing its behavior. It's building a workshop. It's now going to start building some dragons. Yes. And once it's repelled this current attack, it's just going to build lots and lots of dragons. You see it's building or generating instructions for itself. It says build dragons. And eventually, I'm going to let this play out to the end because our final victory here is extremely satisfying. It takes all of these agents and starts generating now, alternating between instructions that say build even more dragons and attack using those dragons. And you know, if we played this right out to the end, you would see that it actually wins the game against this opponent that it's playing against here. So this game, this sort of mini real-time strategy game, was introduced by some folks at FAIR, and there was some follow-up work specifically looking at the use of these kinds of latent language policies in the context of playing this game. And so what they did, this is Hung-Yun Hu and some collaborators at FAIR, is got a bunch of people to play this game, and actually got pairs of people to play the game, where one person generated a high-level instruction that the other person should follow. The other person saw that high-level instruction and translated it into a sequence of lower-level actions. And this was done at sort of a lower framework in a way that people could sort of reasonably be expected to to follow these instructions, but also to maybe remember all of the instructions that they had seen in the past and multitask in various interesting ways. And so they collected this huge data set of people talking to other people while playing this game, and then also the sequences of low-level actions that the actual players of the game were generating, and found that sure enough, if you train a hierarchical model like this that generates instructions and then follows those instructions, you're able to solve the imitation learning problem here much, much more efficiently than if you try to learn from these low-level instructions alone. And so if you restrict yourself purely to imitation learning approaches, we find in the context of this game that something that's trained in this hierarchical way does much better than something that's trained just to imitate these low-level action sequences alone. Now, one important thing to notice about this plot that we have here is that we are still far from perfect gameplay. So this is, I think, numbers when played against the easiest bot that's available for this game, and even against this easiest bot for the game, our learned model, which is learning from these relatively rich human demonstrations, is only able to win 60% of the time, when it ought to be able to exploit this particular agent and win 100% of the time. But importantly here, we're really, we shouldn't expect that we're going to be able to do much better at this game in this imitation learning paradigm. That basically we have suboptimal human demonstrations. And this data set is large enough, and the sort of extent to which this model actually does what the people are exhibiting in these demonstrations is close enough, or is faithful enough rather, that we don't expect to be able to sort of get to 100% win rate on this game just by following the humans here. So we have these human demos. These human demonstrations tell us something about what words mean, tell us something about the space of high-level strategies available to the game, available to us in this game, tell us a little bit about how to implement those high-level strategies, but they're not as good as they could be, and they're not as good as we could imagine, sort of perfect gameplay, even with respect to these high-level actions being generated by our models, how that could be. And so what we would really like is some way to start in the space of human-generated instructions, to start with a sense of what the high-level actions available to us are, with a model that can generate instructions in this way, and still be able to fine-tune this directly on some sort of task-specific loss to optimize now not just for fidelity to our original human users, but also for actual success on this task. And it's very natural to say, okay, let's just take these models that we had before and fine-tune them via reinforcement learning. And this is something that you can do, but the questions then are, one, can you actually do this sample efficiently? And two, can you do it in a way that actually preserves the semantics of this space of high-level behaviors that were originally exhibited in the human data? And as a counterexample, here are is something from an earlier paper by our co-author Mike here that was on learning strategic communication in the context, learning sort of dialogue policies for strategic communication. So pairs of agents that were like negotiating trades and had money and had objects and were trying to figure out how to swap the objects with each other. Same basic paradigm where you get these people, or you get people to play this game. You train models to imitate the people, and then you fine-tune those models via RL. And what you get out are dialogues that look like this, where agent 1 says, I can, I, everything else. Agent 2 says, balls have 0, to me, to me, to me, to me. And empirically, these agents do super well at this task, get to 100% task accuracy, but at the cost of losing sort of any semblance of human interpretability in the context of these games. And in fact, when this paper was published, this was at EMNLP in 2017, and shortly before that, when things went up on archive, it generated probably the one of the worst AI research press cycles, where the existence of messages like this immediately turned into, Facebook has developed a super intelligent AI that communicates in its own language to avoid detection by its human handlers and is going to kill us all. So we would like, I guess, both to avoid developing AI that's going to kill us all, but also just developing AI that's going to shield us from press cycles like this. And so the question is, can we actually sort of do this? Can we get better at this task while maintaining the semantics of these kinds of human messages and avoiding semantic drift, avoiding messages being used by these agents in ways that fail to preserve the original meanings of those messages? I'll note in passing here that there's a huge amount of work that goes on in this, both in sort of work on just like language generation and doing task-specific fine-tuning of models for language generation, and also in the emergent communication literature. The specific piece of this question that we're going to look at, and I'll say here that like most of this work is on sort of designing fancier loss functions or designing fancier models that are in very sort of specific targeted ways able to avoid this particular problem. And the scientific question that we're going to be trying to answer in this next part of the talk is really whether we can get away with less than all of this, and whether we can come up with some much simpler technique that will give us the same benefits, and specifically whether we can avoid the problem of language drift, even in really complicated tasks that like we were looking at before, just by manipulating the task distribution itself. So can we sort of set goals for our agents in such a way that they're able to accomplish our original goals while avoiding semantic drift. And before getting into this in the context of these complicated sort of real-time strategy games like we were looking at before, I want to start with something super simple, the sort of simplest possible example you can imagine of one of these latent language policies, which is what's called a Lewis signaling game. We're now talking not about our co-author Mike Lewis, but the philosopher of language, David Lewis, who was writing several decades prior to the rest of us. The way a Lewis signaling game works is as follows. We have two players in this game, which we're going to refer to as our instructor agent and our executor agent. The instructor is going to observe some sort of signal from our environment that we'll call observation 1 or observation 2. On the basis of that signal, it will generate some kind of message that we'll call message 1 or message 2. It'll send that to the executor agent, and then the executor will take one of two actions in the environment that we're going to call either action A or action B, and represent here as sort of pressing a red button or pressing a blue button. And so concretely, a round of this game might look like the following. The instructor agent is going to observe observation 1. It will choose, based on observing observation 1, to send message 2 to the other agent, and agent 2, on observing message 2 and not having access to this original observation, will then elect to take action 2. And success in this game then is basically going to be determined by some combination of the observation and the action. And so in particular, we can define a reward function that tells us, for every observation action pair that we might have observed, how good was that combination for both of these players. And so here's one possible reward function in this game, where when you see a triangle and you push the red button, you get a reward of 1. When you see the square and you push the blue button, you get a reward of 1, and other combinations obtain a reward of 0. And so what we want in this game is that the instructor agent, when it sees the triangle, is going to send a message in virtue of which the executor agent is able to press the red button. Obviously, there are other ways we can define this reward function. Here's sort of the opposite game, where you want to press the blue button when you see a triangle, and so on and so forth. And finally, because we're really interested in semantic drift today and sort of figuring out strategies for learning in these games that are faithful to the semantics of natural language, we're going to consider a version of this task in which this communication protocol that these agents are using, the space of messages that's available to them, is defined by natural language. And so our instructor agent is going to be able to send messages like push blue, and we would like for the executor, on seeing messages like push blue, to push the blue button. Now, I'll note that the space of messages that you could imagine using in this kind of game is very large. An alternative message that the instructor could also send would be, I see a triangle, and that would be a faithful description of their current state of the environment. And the executor will now need to know at least something about the structure of this task and about the specific reward function being optimized for, in order to interpret this message appropriately. But sort of taking a step back and thinking just about the kind of push red, push blue kinds of scenarios, notice that even if we restrict ourselves to this protocol, there are actually two solutions to this game, right? One of them is that when there's a triangle, the agent says push red, and the agent pushes the red button. And if this happens, everyone's going to get a reward of 1. Another solution is for the executor agent and the instructor agent to sort of collectively agree that push blue actually means you should push the red button. And so when we see a triangle, the instructor agent will say push blue, and the executor agent will interpret push blue as an instruction to actually push the red button, and so on and so forth. And so this is a strategy that you can use in this game. It's coherent. It allows the agents to get a reward of 1, but it is, in the context of this Lewis signaling game, as close as we can come to our sort of Terminator scenario for a couple of slides back, where the agents are exchanging messages in a way that's comprehensible to them, but not necessarily comprehensible to a human who's standing outside the system. Okay, good. So these are sort of the kinds of solutions that we can actually get to. And the question is, how do we actually get to them? Suppose now that we have a bunch of agents that are trying to play this game, and we parameterize them in a following way. My instructor agent is going to have a single parameter that I'm going to call theta I, with the property that, when it sees a triangle, it'll do push red with probability theta I, and push blue, and generate push blue with 1 minus theta I, and that reversed for the square message. And similarly, I'll have an executor agent here with a parameter theta E that pushes red with probability theta E when it actually sees the message push red, and similarly for the blue button. What is the reward that our agents expect to obtain in this game? And if you sort of work this out, assuming that the observations are generated uniformly at random, the expected reward in this game obtained by this pair of agents is going to be exactly theta I, theta E, minus half theta I minus theta E plus 1. I may have a sign wrong in there. I think that should be a plus. But anyway, this is the expected reward in this game. And notice, as we were saying before, that you'll have an expected reward of 1. You'll have an optimal policy for this task, either when theta I and theta E are both equal to 0 or both equal to 1. But we will have something that corresponds to natural language roughly only when this parameter theta E is greater than 1/2. That is to say that usually when the agent sees push red, it actually pushes the red button. And usually when the agent sees push blue, it actually pushes the blue button. And so, the sort of constraint now on the kinds of solutions that we'd like to find in these Lewis signaling games are ones where we get to an optimal policy, and it's the optimal policy that corresponds to natural language in the sense that theta E is set large rather than small. Now, suppose we actually start with a pair of agents, with these sort of parameters theta I and theta E selected arbitrarily, and we try to do reinforcement learning in this game. And specifically, we run a policy gradient algorithm on the expected reward that we have written on this slide. What's going to happen? And what's cool is that this game is simple enough that you can actually plot like the full phase space of the evolution of these agent policies. So if I think of any point on this grid now as a setting of theta E and a setting of theta I, these arrows are basically going to tell us in what direction the policy gradient is going to point, and will let us figure out what final solution to this game our agents are actually going to come to, right? So concretely, if we start up here where theta I is small and theta E is close to 1, we're going to wind up in this top right corner just by like following the flow of these arrows on the chart. One thing to point out here is that we're assuming that these theta E and theta I are bounded between 0 and 1, and that we can do something sensible when you hit the boundaries of this grid. Good. Okay, so a couple of things that we can sort of represent graphically now that we have this visualization of our game. One is that, first of all, we can consider the space of natural language initializations, sort of reasonable starting points that we might expect to get from human data, as anything where theta E is greater than 1/2, as written here. And similarly, we can consider the space of this shouldn't be natural language solutions, but acceptable solutions to the game as ones in which theta E winds up greater than 1/2. Ed, you had your hand up.
I did?
Yes.
Oh, I maybe mistyped something, but
Okay.
actually, while I have your attention, just going back, was there 1 minus, should it have been like 1 minus theta for some of those? Like the second lines should be theta I and 1 minus theta I. And...
No, so like P of push red given triangle is theta I, and then P of push blue given triangle is 1 minus theta I.
Oh, so it's given the right things always.
Right,
Okay,
so,
never,
yeah.
okay, ignore.
Right, so this is actually like there were 4 probabilities that determine an agent policy, and we're assuming that, or rather, there's there's 2 conditional distributions that matter, and we're assuming that those 2 conditional distributions are coupled by 1 parameter in kind of the obvious way.
Okay, I mean, isn't that kind of solving a lot of the learning problems
Yes.
for these? So if you don't have that constraint, okay, I'll save my follow-up question to when you're done talking.
Okay. Yeah, I mean, how things work when you don't have the assumption that your behavior in the case of the 2 observations is flipped is a good question for follow-up. But even with this minimal assumption, I guess for context here, like part of what we're trying to do is really just figure out like what's the simplest version of this game in which we can actually really expect to solve this problem of language drift, and we're going to see that in a minute. Okay, so the point is that I think we can reasonably assume that we are if we have some amount of data that we're able to get an initialization of this policy where theta E starts off greater than 1/2, right? Where we have a little bit of information about the natural language semantics of these parameters. And then we're going to do RL and see what happens. And the important thing is that in this little triangle that we've carved out here, corresponding to like a quarter of what we said were reasonable initializations of this game, we're going to wind up in the bad optimum, the optimum that we were trying to avoid, where blue means red and red means blue. So here's semantic drift. We would like to avoid semantic drift, and as we said before, we'd like to avoid semantic drift specifically by just changing the task distribution and doing nothing else. And so, now we're going to come to the only interesting modeling idea in this part of the talk, which is to just say, what happens if we train on both of these reward functions that we were looking at before simultaneously? So we have, one where red means push the triangle, or triangle means push the red, one where triangle means push the blue. And we're additionally going to make the following assumption that we are now going to structure this set of latent language policies in the following ways. We're going to have task-specific instructors, and we're going to have a task-independent executor that doesn't even know what task it's operating in. Right, so I have instructor 1 associated with reward 1, I have instructor 2 associated with reward 2, and I have a shared executor that's going to try to sort of satisfy all of these tasks together. And notice now that this will only work for languages of the push red type and not for languages of the I see a triangle type, because the executor is not going to have enough information to know which of these things it should be, what the appropriate contextual interpretation of I see a triangle is. Good, okay, now's our setup, and we're just going to optimize the expected reward 1 plus reward 2 simultaneously. And the cool thing here is that, sort of simplifying things a little bit for analysis, where we assume we're going to initialize our thetas the same way. I think this actually goes through even if you don't make this, but the math is a little nicer this way. This is all you need to do to ensure that you wind up at the natural language optimum of this game. Right, is just train on the sort of 2 versions, the 2 interesting versions of the signaling game simultaneously. Whenever you do this and whenever you have a shared executor and these 2 independent instructors, this is enough to, almost surely guarantee that you are actually going to converge to the optimum of the game and not the other one. Because this is 3-dimensional, it's a little harder to look at the flow chart, but you can actually say something stronger here, which is that theta E is independent of the particular value of theta I1 and theta I2, and then basically wherever you optimize it, it's just going to like run in a straight line up to the top of the chart if you initialize it greater than 0.5 and down to the bottom if you initialize it less than 0.5. Okay, cool. So high level takeaway here is just that multitask training of this kind by itself in the context of these Lewis signaling games suffices to eliminate semantic drift in these games. Okay, great. So we looked at our toy communication task now. What does this actually look like if we try to scale it up to more interesting tasks? So let's think about this real-time strategy game again. This original game was sort of cleverly designed in such a way that there's this kind of rock, paper, scissors dynamic, where some agents are strong against some agents and weak against other agents. And so what we're going to do is just generate like a bunch of different permutations of this chart by pointing the arrows in different directions and sort of manipulating the relative strength that different kinds of agents have against each other. And this is now going to give us a large family of versions of these real-time strategy games that we can do in a multitask way. Good. And then we're just going to do RL on this game via policy gradient in exactly the same way that we're looking at in the context of these Lewis signaling games. I want to go get through the results here quickly so that I can get to the second half of the talk, but I'll just say very briefly, there's a couple of ways in which you can evaluate whether this kind of semantic drift has occurred. One of them is to say, well, let's see if these agents are actually able to correctly follow instructions generated by agents that they weren't co-adapted with, that haven't had a chance to learn, one of these secret balls to you kinds of languages. And so if we pair agents that have been fine-tuned sort of against one if we pair executors against if we pair executors that have been fine-tuned against one instructor versus executors that have been fine-tuned against many instructors, you see small improvement. And then we evaluate them on instructors that weren't the ones that they were paired against. You see small improvements. A more explicit way is just to look at a bunch of messages, take all of the messages in which the word, say, peasant or swordman or spearman appears, and then all of the messages in which the agent actually did something involving a swordman or a spearman or a peasant or whatever, and basically measure how much is happening off the diagonal in this joint distribution, and unsurprisingly find that this by a factor of a third or more reduces the amount that's happening off diagonal. And so the agents really are continuing to adhere to the semantics of these instructions and sort of behave in the way that they're instructed. But most importantly of all, you actually get better at these tasks as well. And so if you sort of do this multitask training and you compare to agents that are only able to train against a single task, you do substantially better than those agents. And even if you let yourself sort of fine tune against single tasks for 3 times as long as the agent has had to learn in this multitask setting, sometimes it actually gets to a point where it's able to beat that kind of very focused single task training. So this sort of multitask learning in the context of these signaling games and these real-time strategy games is able to both get you to good optima and to do so, as we were claiming before, while preserving the semantics of our original instructions. And so sort of coming back to the theme that we had at the opening of this talk, the point here is we were able to take a model trained to do instruction following, right? Trained to generate instructions and then follow the instructions. And we were able to make it better at instruction following, sort of more effectively able to do the things that it was being instructed to in the context of one of these games, while sort of maintaining faithfulness to the language and not translating these or, turning these natural language messages into arbitrary subtask indicators that don't necessarily mean anything on their own. Okay, I will pause very briefly here for questions. I don't have as much time as I would like. Am I supposed to end at the hour?
I guess officially, yes, but
okay.
We're happy to run over normally. So
okay, cool. Let's see how far we get through this. Questions on that first part before we move on. Okay, and we can also do questions at the end. Okay, so total shift of gears. The question now is, suppose we have no ability to interact with the world and have only access to text. How much can we actually learn about how the world works anyway from text alone? And so, for those of you who have encountered the paper from Bender and Kohler that was at whatever it was, ACL or NACL last year, complaining basically that you can't get meaning out of text alone. The point of this half of the talk is about trying to get meaning out of text alone. Right, it's an exciting time to be working on language models as an example of why. Here's a passage that I lifted from a Gary Marcus article that has some other problems, but this particular passage is actually kind of cool. We, take some text actually from Eugene Charniak's PhD thesis saying Jack and Penny went to the store to get, or Janet and Penny went to the store to get presents for Jack. Janet said, I will buy a top. Don't get Jack a top, says Penny. He has a top. He will ... And we allow a state-of-the-art language model, in this case GPT-3, to complete this passage. And it completes it in the following way. It says, he will get a top. I will get a Jack atop, says Janet. And there are a bunch of important things to notice about this passage, right? It stays on topic. It knows who is involved in this situation. It knows enough about social conventions that it is Janet who is likely to speak next in this conversation. And we get all of this complicated behavior, again, just from like training text on the internet. And I think, you know, it's easy to forget that as recently as like 5 years ago, this was just not something that language models could do, right? They had access to a fixed context. They couldn't see very far into the past. And they certainly couldn't do this kind of long-range modeling, like remembering that Jack is still around here and that the thing that we're talking about right now is that we're going to get Jack atop. But the other thing that's important about this passage is that it's total nonsense, right? Penny says, don't get him atop. He has a top. He will get a top. Janet says she'll get him atop. And so we're in this sort of wonderful state, right? You know, and this discourse, the sequence of exchanges doesn't correspond to anything that you would ever expect people in their right minds to say. And so we're in this sort of wonderful state right now where language models work like 50%, and we're simultaneously trying to understand how they can even do that well, and how to actually get them the rest of the way towards being able to generate passages like this that are actually coherent. And you know, it is sometimes, if you sort of do a little bit of cherry picking, but less than we might have expected, possible to get even greater coherence. And so the question is, are models able to do this just because they're like really good at modeling surface statistics among words, or are they actually like representing and reasoning about the world that is being described? Well, what would it mean for a language model to represent and reason about the world that's being described? And here's a sort of cartoon of how that might work. When somebody says Janet and Penny went to the store to get presents for Jack, we're going to construct a representation of the state of the world that maybe looks a little bit like this, right? That contains all of the entities and the events that we know about and tags them with their names, and you know, also labels among all of these entities all of the relationships and properties that we actually know about, in the sense that those relations or properties are mentioned by these sentences. I'm playing a little fast and loose with the semantics in these drawings, but hopefully, you know, you sort of get the general gist here. Right, so this is an explicit representation of the situation that is being described by the sentence. And notice also that what this depiction of a situation does is it makes explicit the things that we know and we don't know, right? We don't know whether the top is purple or not. We don't know whether Jack perhaps is the owner of the store and is already in possession of the top, the same top that Janet and Penny are trying to buy him, and so on and so forth. So we're going to call representations like this information states. They represent our current information based on the text that we've seen so far about the state of the world. And as sentences get added to our original discourse, we're going to think of those sentences as specifying updates to these information states, right? So Jack already has a colorful top, tells us now actually in the world there exists a different top. That top is colorful, and that specific top is possessed by Jack. And so I know that this new edge is present, and you know, can infer that various other kinds of edges are not present. And note that, you know, different kinds of updates or different kinds of sentences are going to specify different kinds of updates to these graphs. And so in particular, if Janet and Penny go to the store, they buy a top and they give the top to Jack, we now know that Jack has the top. And this is something that we can infer from the text, even though like Jack has the top is never stated explicitly anywhere. And so we're going to think of these kinds of relations, these things that are sort of implicit results of things that are explicitly described, as also being part of these information states. Okay, so we said that this was a sort of cartoon of what it might look to explicitly represent sort of how sentences pick out worlds. This particular cartoon comes from the dynamic semantics literature and linguistics. In contrast to sort of standard like approaches to formal semantics, we think of sentence meanings now as corresponding not to functions from possible worlds to truth values, but instead as functions from information states to information states. So the meaning of a sentence is the way in which it causes us to update one of these implicit representations of the world. People in the NLP world mostly encounter dynamic semantics in the form of discourse representation theory, and specifically as like representations of argument structure rather than representations of meaning. But viewing these as meaning representation turns out to be super useful for thinking about how those representations might work in current machine learning models. And why is that? Well, you might imagine that if I had access to this kind of world representation, it would help me do all kinds of downstream language processing tasks, right? Language generation, language inference, and so on. Because now, rather than having to sort of reason about relationships among surface forms and relationships among words, I can just like look at my world model and ask whether it's plausible that Jack will get a top in the context of this world model that states explicitly that Jack already has a top. Now, obviously, current NLP models, and specifically these big language models that we're thinking about, don't have like explicit symbolic representations of the world like this. We're not giving them supervision for this, and like more fundamentally, there's nowhere to put explicit symbolic representations like this in a big transformer language model or whatever. But to the extent that we think that these kinds of representations might be useful, it's reasonable to ask whether big language models have even like implicit representations that look like this, even sort of half-baked implicit representations that look like this, that can be used to support language generation and so on and so forth. So let us very briefly put on our language model explorer hats and actually try to find models of dynamic semantics living inside the representations computed by pre-trained language models. The basic paradigm that we're going to use here is as follows. We're going to take a document, we're going to feed it to a language model. Here we're using the BART encoder-decoder model to do language generation. And separately, we'll get somebody off the side to give us a representation of the state of the world as it exists at the end of this document that we're encoding with our language model. And importantly, the language model has never seen this world representation. We've trained it without any of the supervision, and we're just using it to query these models. And we'll now see if we can find some way to read these explicit semantic representations off of the neural representations computed by our language model anyway. Now, an important caveat here is that, obviously, in some sense, these world representations are recoverable by a sufficiently expressive model from the text. And so the extent to which this paradigm is going to actually allow us to say interesting things about language models as language models will be determined by our ability to construct this probe in a way that's too low capacity for it to do any interesting semantic inference on its own. That's only going to sort of reveal to us things that are in some sense already present in the language model. And we're going to see that we can actually build such a probe using nothing but the language model itself and a single linear transformation. So how's that going to work? Since these information states are structured objects, we're going to try to read them out via the individual propositions that they represent, right? So we want to be able to ask of these language model representations, is the door locked? We'll come up with some representation of the proposition door is locked. We'll feed that to our probe. We'll pull some representation out of our language model, and we'll see if we can determine whether it is true or false in the world described by this text that the door is locked. So concretely, to do this, there are three things that we need to specify. We need to specify how we encode these propositions, how we localize information about these propositions within the representations computed by our language model, and finally, how to compare our proposition representation and our language model representation in order to compute a truth judgment. So very briefly, to encode propositions, we're just going to write a sort of template-based thing that transforms the propositions into natural language strings, and we'll encode those natural language strings using the language model itself. And this will give us vector representations of propositions, including propositions that are never explicitly stated by the text. Now, to figure out how to get representations of where these individual propositions might be living inside this text, we're going to build localizers that basically assume that the representations that carry the relevant information are the representations of the initial mention of the objects involved in the proposition that we're trying to decode. So if I'm trying to figure out whether the door is locked, I'm going to look only at representations of the first mention of that locked door in the discourse. And finally, to compute truth values, I'm just going to train a single weight matrix now that on sort of these real world representations and the language model representations that we get as input, and see if we can fit that model to actually compute the truth of these propositions. And so this is the only piece of any of this process that actually gets to update parameters in response to information about what these grounded world states look like, and it's a single matrix. Good, right. So the point here, this linear transformation is really our own free parameter, only free parameter. And we're asking, is there some linear readout of these world states such that, or rather of these language model states such that the world state is recoverable from them? We're going to evaluate in two tasks. The first is this alchemy data set, which involves a lot of reasoning about undescribed state changes, like we were looking at before. Pour the last green beaker into beaker 2, then into the first, and then mix. And what you wind up with is a brown beaker. And we're going to ask questions like, what color is the first beaker? Even though we have, like, the word brown never shows up here, and the identities of the colors of the particular things are never, or for the most part, never explicitly discussed. And then we're also going to look at this text world, like text adventure game data set, where you're walking around a house and the set of actions that are available to you depend on where you're standing in the house. And again, various not explicitly described state changes that are affected by actions that you've taken in the past. So how well can we actually recover these kinds of propositions from our language model? And the cool thing here is that in an absolute sense, we can do quite well, right? So just with this one linear transformation and the sort of rest of the probe that we built before, we can recover, like, in this alchemy setting, I think this is like 75% of object descriptions completely using this probe. And in text world, we can recover close to 90% of object descriptions with perfect accuracy using this probe. And to sort of put this number in comparison, if you don't have access to the text at all, and you just have to guess that sort of every individual object is in the most likely state for that object, you only get to like 30% on both of these tasks. And if you assume that you only get to see the first mention and that these object states never changes, and basically these models can't actually represent updates to the world state, you also do substantially worse. So these models really are able to track object state and changes to object state over the course of a discourse, right, in such a way that you can read these states off relatively reliably from individual mentions. Another interesting thing is to look at what kinds of language models do well in this task. If we train, as we were doing on the previous slide, both take a pre-trained language model and then fine-tune it on one of these tasks, that is best. But you do only slightly worse if you start with a pre-trained model that has never actually seen the alchemy data set or the textual data set at all, and try to recover these representations of object states from those things. And conversely, you do substantially worse if you only get to train on in-domain data of the kind that we're actually using for the probing. So the important thing here is that it's really pre-training and not necessarily domain-specific fine-tuning that is producing these kinds of world representations and entity representations. We also said previously that we were going to construct these probes in such a way that they would look only at the initial mention of these objects and none of the other mentions. We can do this in an even more fine-grained way by, like, trying to read off from individual tokens object states. And in, like, this alchemy data set, it turns out to be the initial description, like specifically of the volume and color of that beaker, that holds subsequent information about the state of the beaker. And it's a little bit less clear-cut in text world, but, like, you consistently can do well always by looking at all of the tokens that initially describe the object and nothing else. And so what all of this, the picture that all of this paints is something like the following, that the initial mention of an entity in a document, once that gets encoded by one of these transformer language models, is going to serve as a, like, global repository of information about that entity. And when we then encode other information about that entity that causes its initial state to change, we're actually going to reach back into the representation of the initial mention and update that representation to now describe the new state of this entity. And what this in turn suggests is that we should be able, one thing that's kind of cool about this is that this picture is almost literally the same as a picture that exists in one of these original dynamic semantics papers that's talking about how sort of representations of entities introduced existentially into a discourse get represented. So I think it's, like, really pretty credible to claim that this neural language model is implementing some version of this Heim-style file card semantics. More importantly, what it suggests is that we can do the following experiment. We're going to take a discourse whose final consequence is that the first beaker is empty. And then we'll take another discourse whose final consequence is that the second beaker is empty. And then we will take the representation of the first beaker from the first discourse and the representation of the second beaker from the second discourse and do nothing else, and ask the language model what kinds of actions it thinks are appropriate in this kind of Franken state that we just built, corresponding to no real text, and just from the representations of beakers that were constructed by manipulating those beakers in other contexts and gluing them together. And sure enough, here, for the most part, this language model is only going to generate things that talk about removing liquid from the first beaker or from the third beaker, and it will never try to mix or never try to empty out the first and second beakers because it thinks those things are already empty based on these representations that were constructed in totally different discourses. Good, and we even have 5 minutes left. So, one very important set of caveats here is that there's all kinds of interesting semantic stuff that we haven't looked at all in this paradigm today, right? We're assuming that there's kind of one of every object and there's no interest in quantification at all. Quantification is super interesting in where does a representation of there are 23 reindeer go and what does that representation look like? And various other, more complicated semantic phenomena that are the main things that people actually look at on the linguistic side of these kinds of representational theories. And finally, the least satisfying piece of the story for me is the relationship between errors in these state representations and errors in the underlying models. So while, when you're in a state that the model or that the probe can correctly recover, sort of indicating that the state has been correctly encoded, models mostly generate correct sentences. But the correlation between errors in the underlying probe and errors in the generated sentences, if you look at it at the level of sort of errors about individual objects and sentences about individual object, there's basically no structure in this relationship at all. And so the one thing that doesn't seem to be true is that we can attribute errors in generation to attribute to errors in the underlying world model. And trying to figure out what's actually going on here is I think, one of the most interesting questions and something that we're looking at right now. Good, but just to sum up, it looks like these big pre-trained language models are learning the rudiments of, real semantic representations that do all of the things that we want representations in formal semantics to do. And they're constructing these representations without having ever seen any kind of information about explicit meaning representations at all. And specifically that pre-training is inducing, highly structured, moderately reliable file card type semantic representations of a kind that are well studied already. And it's then natural to ask, can we sort of rip these world models out of language models and use them for other downstream tasks that don't have anything to do with NLP? And conversely, now that we know how these models are structured, does this give us better ideas about how to do grounded training of language models in a way that will maybe let us get to more reliable language generation? Good, and I will wrap up there and take questions. And let me check my calendar. I am happy to stick around for a little while longer if people have more questions.
Awesome. Thanks so much for the talk, Jakob. That's really great. Yeah, anyone feel free to hop in with questions on the microphone.
Okay, I've got a question.